So, what is endurance limit? Endurance limit is that maximum value of completely reversing stress that a standard specimen can sustain for an unlimited number of cycle without fatigue failure. That means, on the that stress level is such, that means due to this stress level our structure will not fail. If we apply below that stress level, what happens? It can sustain unlimited number of cycle, but that below that stress level you need not to consider. You need to consider which stress level? The stress level which is the maximum one. That means, what happens? Let us consider, let this is a structure, this is a structure. So, it is subjected to let us P 1 or sigma 1, sigma 2, sigma 3, sigma 4, this types of stress. So, it is observed that sigma 1 is greater than sigma 2, greater than sigma 3, greater than sigma 4. What I am telling, understand? So, sigma 4 is less, much less. Beyond this sigma 1 stress, if you increase that stress level, it will not subjected to unlimited number of cycle, it will have a limited number of cycle. What is called that stress? That means, this above this sigma 1 stress will not consider as a what is called endurance limit. So, what is endurance limit? Endurance limit will be this sigma 1 stress, because above this stress what happens? Your structure is subjected to some limited number of cycle, whereas this sigma 2, sigma 3 which is fast lesser than this sigma 1. This sigma 1 if you apply in this structure, it can sustain unlimited number of cycle, but this sigma 2, sigma 3, sigma 4 is not the endurance limit. Endurance limit will be that maximum, or you can say optimum value of that stress level. After that, if you increase stress, it will have some limited number of stress cycle. How we can predict this endurance limit? Because this endurance limit is a very important property for fatigue analysis. How generally experimentally we can find this endurance limit? This endurance limit can be determined by means of a rotating beam machine. This rotating beam machine was developed by a scientist whose name is R. Murray. That is why what happens, this machine also sometimes called Murray rotating beam machine. Okay. Here generally this experimental setup, here I am showing, here you can see this experimental setup generally is rotated by a electric motor. You can see this is a electric motor, and this electric motor how much revolution it is subjected to, that thing is recorded by a revolution counter. You see this is a revolution counter is there, how much rotation is there, that we can count. With this you see here the specimen, here the you see rotating beam specimen generally here we put. This rotating beam specimen is subjected to a weight, you see this is the weight, how it is subjected to weight. This is generally here I am showing, it is subjected to weight like this is a hanging device. By this hanging device here generally we apply the load. With this load is applied such a way in this component, so that this specimen is subjected to what? This specimen is subjected to pure bending, pure bending. That means, this specimen is not subjected to any types of shear load, any types of shear stress should not be there, it is only subjected to bending stress. What I am telling, understand? So, this specimen have a very specific or special types of characteristics, or it has some special types of dimension also. The specimen here I am showing, you need to prepare this specimen according to this dimension and this shape, this you should keep it in mind. Now, you see this specimen dimension here I am showing, at the middle position you see it has a diameter of 7.5 millimeter, is unit is in millimeter, and you see here this specimen have a curve types of shape, this curve surface radius is 250 millimeter, this you should keep it in mind. Okay. So, when you manufacture this specimen, these are the things you need to follow, and the overall dimension of this specimen is 85 millimeter, you can see, and it is subjected to a bending moment MB, you can say this is pure bending moment. This is a little bit I am just giving you an example of this pure bending moment, like you see, let us consider this is a beam. What is beam? You know very well. Okay. Beam means which is subjected to a load transverse to the axis. Let this is our axis, x axis. Once the load is acting transverse to this, then this is generally called, you see, this is generally called beam. Now, in this case, generally if you draw the shear force diagram, let this is a beam P P, it is subjected to load P P like this. Now, if you draw the shear force diagram, how to draw the shear force diagram, you know, I am just drawing this shear force diagram, here it will be 0. After that you see there is no shear force, after that here there will be due to this force P, there will be P here, after that this is like this. Okay. Now, if you draw the bending moment diagram, you will observe that it will have a bending moment, generally you can see it will have a bending moment from here to here, it will be like this. After that this mid range, let this is A, B, C, D. So, this mid range have a bending moment, this is called shear force diagram SFD, and this is called generally bending moment diagram BMD diagram. So, in this mid portion of this beam, you can see it is subjected to a bending moment MB, which is generally constant. That means, this BC then this BC portion, here you see this BC portion, here SF is shear force is 0, what I am telling, understand. Now, what is bending stress, you know, sigma B is depends on bending moment into distance from neutral axis y divided by second moment of inertia. I have already discussed this thing in previous lecture. So, this bending stress, generally whatever this specimen is there, this specimen is act like this BC portion of this beam, BC portion of this beam, this you should keep it in mind, because it is subjected to only pure bending. Okay. This you should keep it in mind. How pure bending is coming? Because there is no shear force or shear stress, it is only subjected to this bending moment MB, you see, and that bending moment also constant. How it is, that I am showing on example. Okay. Now, how to calculate this or how to predict this endurance limit, that procedure now I am going to discuss. So, this specimen which I am showing, it is subjected to a constant bending moment, this you should keep it in mind, it is subjected to a pure bending moment. This bending moment magnitude generally we vary, or we generally vary this what it is called magnitude of bending moment by changing this weight, whatever the weight W is there, this weight variation, by the varying this weight you can what it is called change the magnitude of this bending moment, this you should keep it in mind. Okay. Now, for determining this endurance limit, what are the steps we need to follow, that I am just showing, you see. So, first of all, generally to determine the endurance limit, a large number of tests are carried out by using this what it is called RR Murray test, or you can say rotating beam machine. Here generally first experiment is done by considering the bending stress, which is generally kept slightly less than the ultimate tensile strength of the material. So, whatever the bending stress here we are considering, this bending stress just slightly lesser than sigma ultimate strength. The first test generally we used to do by this Murray test. So, based on this sigma b value, or you can see whatever the bending stress we are applying, that bending stress is applying by applying this load W or weight W, this I have already shown you. So, based on this sigma b value, which is little bit lesser than you can say ultimate strength of that material, we generally used to find what are the number of cycle it can sustain. So, here due to this very high load or high bending stress, here this number of cycle will be very less, what I am telling, understand. So, after that generally we gradually what it is called reduce that bending stress level by reducing this load value W. So, this way generally we used to do lot of number of tests. So, first test generally you should keep it in mind, it is started very close to the ultimate strength of that material. After that generally we gradually reduce that stress level by changing the or reducing that load value. So, we record the number of cycle. So, that is why here I have written. Then the stress is slightly reduced and second test is carried out. So, the procedure is then carried out for a large number of tests. Okay. This you should keep it in mind. Like let us consider corresponding to sigma 1 you are getting n1 number of cycle, sigma 2 bending stress, n2 number of cycle, like this way just let us sigma n corresponding to n number of cycle you got. Okay. This stress versus number of cycle generally we need to plot in a log curve. Here you see this curve, here I am showing this log curve. What does it means? So, you can see these things very nicely, little bit I am just showing here. So, this horizontal axis represent log 10 base number of cycle versus this is generally you can say log SF. What is SF? SF means fatigue stress, fatigue stress, that means fatigue failure stress. Now, you see, so if you just plot these things you will get some point, because initial stress if it is high. So, here its number of cycle will be less, then we reduce that stress value, then second point you got that this is first point, second point, like this third point, fourth point, fifth point. After that you will observe that after lot of this n number of tests you will observe that after reducing that stress value your what it is called, your number of cycle is generally not reducing, it is not failing due to fatigue, that you can say, or unlimited number of cycle. Now, if you draw this point, so you will get a generally which is a curve which is looks like this. You see, initially it is generally decreasing in nature, after that it become asymptotic or it become horizontal. So, if the stress level here, that means below this stress level, you see it is not fail, that means this can sustain unlimited number of cycle. Even so, this is a stress level, this I am representing log SE, this stress level I am representing log 10 SE. Though this stress level at which it can sustain a, that means your this load versus, or you can say stress versus number of cycle become a horizontal line, that means it can sustain unlimited number of cycle, that you can say maximum stress value SE is called endurance strength of that material. In case of steel material, it is observed that after 10 to the power 6 cycle, as it is log 10 n, So, log 10 n means if it is n is 10 to the power 6, it will be 6, that is why here I have put is 6. So, it is observed that after 10 to the power 6 cycle generally, or you can say at a level of 10 to the power 6 cycle, this line become horizontal. What I am telling, understand? That is why I have written here, for ferrous material like steel, the SN curve become asymptotic at 10 to the power 6 cycle, which indicate the stress level corresponding to infinite number of stress cycle. What I am telling, understand? So, after this 10 to the power 6 cycle, you see what happens at 10 to the power 6 cycle range, whatever the stress is there, it can sustain unlimited number of cycle. If you further reduce the stress level, your number of cycle become unlimited. So, this is for steel material, whereas some other material is there like aluminum. For aluminum material, generally you see this SN curve. The SN curve means log fatigue stress versus this is number of cycle, like aluminum material. Here generally you see the SM curve is, this is your 10 to the power 6 cycle. After 10 to the power 6 cycle also it is declining in nature. That is why here I have written, for non-ferrous material like aluminum, it is observed that SN curve slope gradually, generally even after 10 to the power 6 cycle. So, the material do not have a limiting value of AC in true sense. In this case, the AC is expressed as a function of number of cycles. So, some non-ferrous material are there, some of the material can be some aluminum alloy also is there, or pure aluminum generally. Here generally you can say your endurance strength is a function of number of cycle. Here the line is not becoming asymptotic or horizontal, it is further declining in nature. This SN curve diagram also is called Euler diagram, because this diagram was published by August Euler, a German engineer, in 1870. This SN curve was developed so early, you see, nowadays also it is very popular and it is widely used. Here one thing you should keep it in mind, whatever the endurance strength we are calculating for steel, that is AC, it is not exactly a property of material like yield stress or ultimate strength. This you should keep it in mind, because for a particular types of material there is a constant yield stress and there is a constant ultimate strength. This is there, but this endurance strength generally is not a constant, you see, it is not a constant property of that material, because this endurance strength is depends on different factors. It is depends on surface quality of the component, it is depends on temperature, it is depends on what it is called environmental condition. So, it depends on different factor. So, as it is varying with different factor, that is why it is not a constant property like yield stress or ultimate strength, which is actually a constant property for a particular types of material. That is why here I have written, in true sense AC not exactly a property of materials like ultimate strength or yield strength, because it is affected by different factors which I have written here. Okay. Now, here we need to know whatever the specimen generally we use for this RR Murray test, this specimen should have very well standard surface quality, well standard dimension. The dimension details I have already explained. Then what should be its surface quality? Its surface quality should be very fine polish, you can say, and generally this polishing should be such that this final polishing is done in axial direction in order to avoid circumferential types of scratches. What I am telling, understand? That means you see, there can be due to machining, there can be some circumferential types of scratches can be there. So, what happens, the final polishing of this R.R. Murray or rotating beam specimen is such, here generally this axial types of polishing is done. This axial types of polishing if we will do axial direction, then this circumferential types of this scratches will be vanish. These types of very high quality polishing is required, what I am telling, understand. And how this specimen generally subjected to what is called bending stress, that related thing little bit I am going to discuss here. Let us consider the cross section of this specimen. Let this is the specimen, or you can say this R.R. Murray specimen. This R.R. Murray specimen, you see, as it is subjected to pure bending. So, you know, in case of pure bending, along the cross section if you take, generally bending stress is bending moment MBY divided by I. So, y is, let us y axis is this. So, generally that is why if the bending moment is like this, that means if the bending moment is hogging type bending moment means the beam will be subjected to bend like this, that means top fiber is subjected to tension and bottom fiber is subjected to compression. Okay. It has a neutral axis, you see, it has a neutral axis. Neutral axis means it is not subjected to any bending stress. So, if we draw the bending stress, you see here the due to this y distance, here y distance maximum is top fiber, you see maximum is, let us from here to here is y 1. So, here once it is y 1, then what happens, it will give you sigma max, and it is linearly varying with y, it is linearly varying and it is become 0 at center in this diagram you can see, and after that at bottom fiber it is subjected to compressive stress, which is other direction I am showing, here you can see. Now, generally in this beam, if you take the cross section, here let us consider this is the cross section, here I am showing. Now, if you consider in this cross section of this beam a point A, let us consider here a point, I am considering A initial position. This A, once this A point, I am taking a point A, let the initial position of A is along horizontal direction. So, initial position, let us first position is at A1 position, second position at A2 position of this A point, only one point I am considered. This only one point, how it subjected to a stress, bending stress, that I am just going to represent, and 3 point represent A3 and 4th point represent our A4 point, what I am telling, understand. So, while this A point is at A1 position, at that time you see from this diagram itself you can see it is this A1 position, you can say your bending stress equal to 0. Let us anti-clockwise direction once is rotate 90 degree, then at this 90 degree rotation its this A point goes to A2 position. So, once this A point goes to A2 position due to rotation, then what happens, here sigma b will be sigma maximum, and which is tensile in nature, you can say this sigma bending stress will be maximum and which is maximum tensile stress. After that, if you further rotate anti-clockwise direction another 90 degree, it come to this A point come to a position, that is A3 position. Here again it is horizontal axis and along the neutral axis this section is. So, here generally again this sigma b become 0, and after that if you rotate another 90 degree, then this at A4 position, where generally sigma b will be generally sigma minimum, which is compressive in nature, what I am telling under, which is this A4 is compressive in nature, you can observe this thing. So, this generally load diagram here I am showing also how it is varying with different angles. So, this a point on this beam specimen generally subjected to due to one revolution, how it subjected to a stress, that I am showing. So, this one point itself is subjected to a 0 value of bending stress, maximum value of bending stress, again 0, again its maximum, and finally again it will 0. So, it is how it is varying, that things here I am showing. So, due to these things you can say each and every point of that beam generally is subjected to a what is called sinusoidal types of loading in this Murray specimen. So, for one revolution how it is subjected, that I am showing. So, one revolution, this one point is subjected to how this fluctuating load or sinusoidal load is subjected, that I am showing. So, this you should keep it in mind. This load generally for one revolution. So, if it is subjected to n revolution, so n number of time these types of loading pattern is there for a particular point generally. This you should keep it in mind. There are some other process also can use, experimental process we can use for measuring the or determining the SN curve. This is another equipment, that is name is high electromagnetic tester. By this high magnetic tester also we can find out the what it is called SN curve. Here also generally you see the testing material that is generally subjected to fluctuating types of loading, you see, and here there is a generally magnetic types of, you see, tester is there. This magnetic tester with there is a chuck is there, this chuck is generally subjected to some rotation. Due to this rotation generally it is subjected to some fluctuating types of loading and number of cycle, what I am telling it. So, this is the example of this another process or another setup for determining the SN curve, what I am telling, understand. Now, so we got the idea about SN curve. Now, we will discuss from this SN curve generally how we can distinguish different types of categories of what is called fatigue. So, depending upon the number of cycle, generally this fatigue is grouped into 3 different categories, that is better to say. What are those categories? These 3 different categories, one category is called low cycle fatigue, another category is called high cycle fatigue, another category you can say is called infinite cycle fatigue. So, how it is look like little bit I am just showing. So, in case of this log n, and let this is our log SF. Why it is called log SF? Because SF is called fatigue stress. Fatigue stress, why it is called? Because fatigue stress, if the magnitude of fatigue stress is high, then what happens, to fail that specimen it will take less number of cycle. Okay. That is why here you see, if we just draw this SN curve little bit here I am showing, then it will be very clear to you. So, here you see this is generally log, this point represent log sigma ultimate, okay, and this point represent, you see, yield strength, yield strength. After that, so from here to here you see, here generally it is, if it is ultimate stress, at that time generally this specimen will no number, you can say 0 number of cycles. So, that is why here I have written 0. From here to here this is 3, as it is log curve. After that here it is 6, after that here you see number of cycle is increasing. Okay. Now, from here to here, this that means up to 1000 cycle or 10 to the power 3 cycle, this zone is called low cycle fatigue zone. LCF. LCF means low cycle fatigue. Okay. This zone is called low cycle fatigue. So, after that means at low cycle fatigue the number of cycle varying up to 10 to the power 3 cycle, that means 1000 cycle. So, in this zone you see it is here the stress level is varying from ultimate stress to yield stress. So, what types of strain here will be? So, here the strain will be generally plastic type of strain. So, that is why it is called plastic region. Plastic region. Now, here you see, so this is generally called low cycle fatigue. So, the low cycle fatigue is subjected to what? Plastic types of straining. Why? Because you see, if you draw the stress strain curve for steel, let this is your stress, this is your strain. What you observe? This is yield, after that generally you see it is coming. So, from yield to ultimate whatever it is or till breaking point, you see this zone is generally, you see this zone is plastic zone, plastic deformation zone. Okay, correct. So, if the stress level is varying from this is ultimate stress to yield stress, within this zone generally what types of deformation we got? Plastic types of deformation. That is why this low cycle fatigue zone is subjected to plastic region or plastic types of straining. So, first of all you got what is low cycle fatigue. Low cycle fatigue means which is subjected to a number of cycle which is within 10 to the power 3 cycle. Here one thing you should keep it in mind, if our point is within below this SN curve, this is generally called safe point, safe region. Below this line is called safe region, and whatever the point outside of this is called failure point, failure point. These are the things you should know. Now, from 10 to the power 3 to 10 to the power 6 cycle, this is generally known as high cycle fatigue. So, in this zone here you see the load varying from yield strength below the yield strength. You see the load is varying here in this zone. In this zone the stress level is, you see, below the yield strength. So, that is why this zone is subjected to elastic types of strain. That is why this zone is, you can tell as elastic region, elastic region. And after that you see 10 to the power 6 cycle, from here to here this stress is called generally endurance strain, strength. So, after that generally you can call, if the stress level further reduce, then what happens, whatever the region you got, that is called infinite life region. This is also a region where elastic deformation is taken place. What I am telling, understand? These are the things you should keep it in mind. So, the fatigue life cycle can be grouped into 3 different group, you can say. One is called low cycle fatigue, high cycle fatigue and infinite life cycle fatigue, or sometimes generally in some book this high cycle fatigue is generally combined with infinite cycle and it is combinedly called as high cycle fatigue zone. Okay. This you should keep it in mind. Now, what is the difference between this low cycle fatigue and high cycle fatigue? That little bit I am just telling. I have already told you low cycle fatigue generally characterized by plastic deformation, whereas high cycle fatigue generally characterized by elastic deformation. Generally the number of cycle in case of low cycle fatigue is low, within a range of 10 to the power 3 cycle, I have already told you, and in high cycle fatigue it is above 10 to the power 3 cycle, you can say. Generally low cycle fatigue, I have already told you, it's involve plastic yielding at some localized area of the component. So, that is why there are some theories of low cycle fatigue is available. Generally for low cycle fatigue we use what it is called a strain life approach. For low cycle fatigue life calculation we use strain life approach. What is strain life approach? That I will discuss in detail. And here one thing you should observe that this low cycle fatigue region varying within a range of ultimate strength to yield strength. That is why what happens here, what we use for designing this low cycle fatigue, here we use a high value of factor of safety. That is why I have written here we use greater value of factor of safety. And this component which is subjected to low cycle fatigue, here generally we design by strain life approach, where generally we use the basis of ultimate tensile strength and yield strength with suitable factor of safety. This you should keep it in mind. Whereas the component which is subjected to high cycle types of fatigue, here generally the design is based on the basis of endurance limit, and here we use this endurance limit approach. Here generally we use SN curve, Soderberg line, Gerber line, Goodman diagram are used in the design of these types of component. What are those things? SN curve, Soderberg, Gerber, Goodman, these in details we will discuss in subsequent lecture. And in this high cycle fatigue we use generally stress life approach. So, in detail this strain life approach and stress life approach we will discuss. Now, in next slide I am going to show some example of what is called low cycle and high cycle fatigue, where generally this low cycle fatigue and high cycle fatigue is taken place, that I am going to show. Generally failure of like stud on track wheel, failure in set screw for locating of gears on shaft, or some you see failures of short lived device such as missile. So, these are the some example which is related to low cycle fatigue. So, where generally this strain based approach is used for fatigue life prediction of these types of component. Apart from these types of component, the welded joint also is one of the very important component. Generally the welded of steel structure which are subjected to a cyclic loading condition which is varying from high cycle fatigue to low cycle fatigue, even extremely low cycle fatigue also it can subject. That welded joint can subjected to high cycle fatigue, it can subjected to low cycle, even some welded joint are there which can subjected to very extreme low cycle fatigue also. Some of the example of high cycle fatigue here I am showing, that is generally the failure of machine components such as spring, ball bearing of gear or gear you can say, that are subjected to fluctuating stresses are some of the example of high cycle fatigue. So, this all about today's lecture. Next lecture I will start from this. Thank you.